Hello, and welcome to another edition of our SIGGRAPH webinar for machine learning and neural networks. So hope you had a great weekend, and I know there's not enough days in between for you to practice, and we went pretty quickly last time. So I just wanted to make sure that we cover everything that we said we will cover, and then that you're understanding at the same pace as well. So before we begin today, again, reading the ACM anti-harassment policy. Please exercise consideration and respect in your speech and actions. Refrain from demeaning, discriminatory, or harassing behavior in speech. Be mindful of your surroundings and of your fellow participants. And alert the community leaders and moderators if you see a dangerous situation or someone in distress. And be excellent to each other. All right, so again, this webinar is brought to you by SIGGRAPH University. We'll send out a survey at the end of this course to see if you want to hear more about the kinds of things we are doing to help people learn and continue their learning, and other mentorship opportunities as well. So thank you to everyone who made this possible. Again, a lot of people behind the scenes working really hard to bring you this webinar, and thanks to you for attending this. I know it's an hour and a half out of your schedule. You come to learn, and hopefully we're learning at a great pace. So this is the third in the last session. We covered a wide variety of things already, and today we are going to look at generative networks, how networks generate images from seemingly nothing or from text prompts. And we'll go over some of those architectures. And then just to tell you where the files are, they'll be posted, the links will be posted in the chat also. So I also uploaded last time's lecture as a PDF, so you can look at the slides, and right after this class, I'll upload this particular slide deck as well. So the files are in different dates. So we have a little bit of unfinished business from last time. We need to cover some of those materials. So we'll go over the files first that were there on Friday. Again, just a brief course overview. And last time we covered a bunch of things. Today we hopefully will cover more of the things that we could not cover last time, including variational autoencoders, and then we'll go on to learn about CNNs and transfer learning and the generative models with GAN and diffusion and transformers. So the last three, they're a little complicated, so we won't run them because they take a long time to learn. So we'll just go over those architectures, and then I'll wrap up with any comments or questions around things. So the questions, we had some questions. So I just kind of summarized a bunch of questions together into three questions around optimizers and softmax and activation functions. So people had asked, like, what are the different kinds of optimizers? So optimizers are, when you are doing gradient descent, there are different ways to do it. And we choose between different algorithms based on primarily optimization for time, like how fast these things converge, how easily the weights are distributed. So again, don't worry too much about them. They're like essentially a technique for making convergence faster. So there's nothing magical about them. They are taking the weights and then trying to see how to adjust them best. So when you do the gradient descent, essentially you are doing a differentiation and then trying to see which way to adjust the weight. So again, don't worry too much about them. They're just like, think of them as an optimization technique. You can't go wrong with one or the other. It's just how fast you can converge. Second question was around softmax. So softmax is just a fancy name for exponential normalization. So when we did the cross entropy for classification, what you get out of that is a log likelihood. So log likelihood numbers, they are kind of unbounded. They can range from -50 to 50. So what softmax does is it does two things. One is that it brings them all into the range of 0 to 1. And then also, because it's an exponential normalization, it pushes lower value much lower, higher value, much higher. So then it's easier to kind of distinguish between them. Ultimately, because they're in the range 0 to 1 and they all add up to 1, using this softmax normalization, you are able to treat them like probabilities essentially. So that's just a technique for normalization. And another question was around like why there are so many activation functions. So remember, the primary purpose of activation functions is to introduce nonlinearity. So you have your input, you sum them up, multiply them with weights, and then you apply this activation function. The ideal function is the sigmoid, which kind of serves the same purpose as the softmax. It kind of pushes things up into 0 and 1 range, and then also because of the shape of the curve, the smaller values become smaller, tend to 0, and the higher value become higher. So the RELU, or the rectified linear unit, is an optimization for that. So because the sigmoid involves an exponential function, it can be a little bit hard to compute and takes a while. So RELU is just a way for us to kind of optimize on that. It provides a similar functionality. It pushes, instead of pushing the left side to smoothly to 0, it just does an abrupt to 0. And then leaky RLU is similar to RLU, but it does it slightly differently. Instead of going straight to 0, it has a slight slope to it. Again, optimizations, just always think of activation functions as introducing nonlinearity into your network. Okay, so before we get into generative adversarial network, let's finish up our business from last time. Any questions on the answers or anything while I switch the slides? Okay, looks like there are no questions yet, but please keep them coming. And always, you'll learn more by asking questions. Anything you have doubt about, just ask it. Like a lot of people would probably have the same questions, but they're too shy to ask. So last time we looked at CNNs, and then I talked about how this convolution operation happens. It's happening in multi-dimensions in the depth side, and it kind of like takes the averages of the pixels or does some other operations on a neighboring set of pixels, and then it replaces those, say, in this case, 9 pixels by a single pixel that has that average value. So it has this effect of kind of compressing your image into smaller things, but overall, it extracts the features out of that image. And then if you do it a number of successive times, now you have at each layer, you would have going from fine details to higher and coarser details about the image. So you might get like ideas about simple circles and lines in the first few layers. And then as you go higher up in the network with more convolutions, you would see like larger features emerge, like shapes that are more distinguishing about the. So again, they become smaller, but they kind of capture the features. So these things are called feature maps. And then you have to remember that all this network doesn't go away. So every layer is there when you train. So as you train it, and all the weights are there. So after you have trained, you also don't throw away the network. So the result is, in the end, is the set of weights. So that is the model. So the model, after it's been trained, the thing that you use to infer later is actually this set of large weights that's the weight at every node that you have picked. So there may be like hundreds of thousands of these weights, but because all we are doing is a simple linear math of weights and input, we can do this pretty fast in parallel on high-speed computers. And this, like, because the matrix math kind of is very nice to be done in parallel. So there are a lot of optimizations in TensorFlow under the hood that make all these things really fast. So the inference should be really, really quick. The training, it takes a long time. So let's take a look at, again, we started doing some denoising in the file there. So this time I loaded up the file beforehand, so there's no time wasted in loading up the data set. So we load this data set up. It's basically a bunch of images from satellite. They're labeled. We won't use the labels for now. And then I talked about how we add noise to the patches. And we also talked about how we are going to extract smaller patch sizes because otherwise the training takes too long. And having more smaller patches gives us more data essentially. So it generalizes well because we're adding noise and we're training for noise. So it doesn't matter what the actual image is as long as we have a before and an after, like with noise and without noise, so we can train it. So we can take smaller patch sizes. We can take even smaller patch sizes. We'll have more of them. So each of these images is 256 by 256, and they yield 4 128 by 128 patch by using this example. And then what we did was we created a noise image of the same size as the original patch. And then we took the noise and added that to the original image. So basically we're left with two patches now, a noisy patch and an original patch. So let's go ahead and system is good. Let's execute that. That's the images, and let's just make these functions. These are functions. They're not executed yet, so we're just defining them right now. And then we can do a sanity check on the size of this network. So it's huge, right? So it's got over 6 million nodes now because of the size of the images that we have. So that's pretty daunting if we were to create a fully connected network for this. So we're going to take some data to train, some to test. And what happened here? TensorFlow is not defined, so didn't do this. So this TensorFlow time to time kind of resets your machine so that you don't hog the machines. The data is still there, luckily. Okay, so that got executed. So what basically we did was the flat map. Essentially, I talked about last time, a map function takes its input and applies this function to each of those inputs. So the train data set is our input in this case, and then the extract patches is the function they're going to apply. And they're going to do the same thing for add noise as well. So then we do that, and then we do a display of these patches with noise added. So I'm going to print just the noise image and the original right after that. So you can see these. We took 5 examples from this. You can see the noise has been added. Can you see that noise is added? So you can see the sprinkles of noise here. So that's now our training set is ready, and we can train this now. So what we did was when we did all these functions for add noise and extract patches, nothing actually happens at that time. So things only, so this is only setting up the data pipeline. So things only come into action when we actually train. So this is a great thing about TensorFlow data processing, that you can set up these data pipelines. They can be complicated. They can be doing a lot of things, but none of this gets executed until you actually use the data. So this is all like you're still setting up the data. And the great thing about this is under the hood, you could have gigabytes of data and it will just figure it out. So it will prefetch some data. So it will always have data to feed you, because in real world training, you might have like 100,000 images and of like they're 500 by 500, and getting them to you will kind of your bottleneck would be reading and loading data. So all this stuff that we did basically prepares the data so that it's being constantly fed to your network. And TensorFlow and other toolkits as well, PyTorch, they'll have this nice data processing pipeline under the hood that you can use to kind of train and bring in lots of data. And it will parallelize it. It will do whatever it can to take advantage of whatever kind of machine you have at hand. So next, we're going to create a model. So this is our CNN. And then I'm going to create just to compare like another model, which is kind of like an autoencoder. So we have an autoencoder and at CNN, we can compare then contrast the two. So let's look at the CNN model. So because of the averaging that happens, you have relatively fewer number of nodes in the CNN, whereas the autoencoder has a very large number of nodes. So imagine this, like using an autoencoder or even a fully connected network for solving these kinds of things, it would take a very long time. So compare that to like more than 1.5 million nodes compared to 20,000 nodes. You can train anything with a fully connected network. It's just that it's going to take much longer. So the convolution not only kind of reduces the number of nodes we need in the network, but it also kind of does this high-level image processing that is nice. It kind of extracts the features out of the image. So this can be sometimes misleading because it is doing a lot more. Even though there are fewer nodes, it is doing the averaging. It's doing the reformulation of the shape of your data. So there's a lot more that is happening. So it's not just apples to apples comparison with nodes, but still, I think it's a 2 orders of magnitude difference in there. So we're going to use the CNN model. And then all these model is a class in Keras or TensorFlow. So we can assign it to a variable and you can just call methods on it. We compile that using an optimizer, and loss is mean average error. And now we're going to train. So this is where things start getting red. And we're going to train for 10 epochs with 10 steps per epoch. So this will take some time. It takes about, so again, it's going to do 10 epochs and 10 steps. So the batch size is 10. So it's going to take a while. So in the meantime, I'll just describe quickly, like this is just engineering. So I'm just writing some code to plot this thing so we can compare these images. So we're going to plot the noisy image, the reconstructed image from our training. We're going to display the ground truth because we know the clean image, that was the original image we fed in. And then we're just going to diff them. We're going to diff them and see what was the, because sometimes it's hard to tell just by looking at it, what the difference is between corrected images or predicted images versus the ground truth. So we're going to just do a pixel-wide difference between the two images. And that's it. So let this train, and then it will we'll come back to this once it's done. So I'm just gonna go ahead and execute these so that when we come back, it's all ready. It's just like a baking show when you take things out of the oven when they're ready. Okay, let's take a question before we switch. So why are log likelihoods being converted to probabilistic numbers? So the reason I talked about in the beginning of the class where I took some questions there. So log likelihood, as I said, is like going to be unbounded range, and you want to convert them to a 0 to 1 range. But at the same time, you also want to push like 0s closer to 0, 1s closer to 1. So you do a softmax or exponential normalization. So how are you getting the pop-ups? So one thing that might help is use Google Chrome. This whole collab Google thing may be one of the reasons. you can also look up the API in the respective toolkit. So what loss function are you using for CNN denoising? We use MAE, or mean average error. It's just a little bit faster. The normal ones you want to use in practical methods is the mean square error, but because it involves taking squares, and we just use MSE because it's just a little bit faster. And that was answered. That was answered, kind of. So do you know the state of the art of denoising work? So state of the art of denoising work is dependent on the application. So there are, as I see it, like if you just think of denoising itself, there's a lot of application in rendering, right? Because ray tracing is the now most used method for rendering, and you can train noisy images because you can always generate the ground truth by letting the render run forever. And so that's like one of the bigger applications these days. And that does use, so it doesn't use CNN, so it uses something called a ResNet, which I'll talk about briefly, but it's essentially a CNN with added stuff. That's what you can think of it as. CNN in practice will smooth out a little bit of the finer details. So what they do is they connect back from the first layer onto the next few layers. So there's just extra connections in there that forms like a U shape. So that's why it's called a U-net. Essentially, it is a CNN actually. So there are other methods for denoising which are now becoming state of the art, like more in the diffusion based models. And I'll go over those later in the class today. So it looks like we're close to finishing the training. Any other questions? It's a great time to answer questions because this thing is computing. It's in the last epoch. Are we going to see results by comparing CNN with autoencoders? I'm not sure what kind of results. Like if you are asking whether today we're going to see, we're not going to run with autoencoders because, as you saw, the size of the network is huge. It's going to take hours to train. But you can you can verify it yourself if you have time. So I wouldn't run it with an autoencoder or a fully connected network just because it's just wasteful. We have a CNN, which is kind of perfectly suited for all kinds of image based training and designing neural networks around images. So I wouldn't use autoencoders unless you wanted to compress the image. So next question, because we have to work in smaller patches, are there approaches to stitching patches back together without seams, like overlapping patches? So the good thing about this thing is that you train on patches, but you do the prediction on full size images. So once you've trained it, it should be size invariant because what you have learned is to denoise, and the seams don't come into play in that case. In some kind of specialized training, like non-denoising, you may have issues like that, and you can overlap where we had the strides where we took the patches at exactly the patch width and patch height. So you get 4 equal non-overlapping parts in our patch size. But you can use other strides, so you have overlapping patches. So that way you can train, if your data is dependent on this overlap, then you can train it that way also. How do you estimate the time will be spent on training the model? So it's, again, as you can see, it's a function of the amount of data you have and the size of network you have, both the depth and the number of nodes per layer. So, and then you can just do an estimate because everything is a number. Each node is a number. So if you think of an image, so it's a, say it's a 500 by 500 image, and it's a RGB, so 3 channels per pixel. You think of each pixel component as a number, and that's what your input is, or that's what your feature is. So if you multiply 500 times 3, that is your input, number of input nodes. So you need minimum of that. And then you have whatever your network is. So based on that, you can do a pretty good estimate. As you see, this particular thing like is taking 33 seconds per epoch. And it's fairly fast, actually. So in reality, in actual practice, people train for a couple of weeks. And not only that, they're training on very high-end GPUs clustered together. So this is, by comparison, a very, very, very tiny network. So this is, you're not going to run like normally if you're in a job, you're going to be running multiple of these models and training them separately. So then one is ready, you're going to start on the other and so forth. And you would, after every epoch, you will look at the loss. And if it is not going down, then you may need to adjust something so it's not like a one and done. So it's a constant fiddling with numbers and changing hyperparameters. That's what people in these jobs do. Okay, so looks like our training is done. We're going to predict on 3 of these and show the results. Sorry. So here's our answer. So we have a noisy image and a denoised image and the ground truth of the same thing. So because we didn't train for too long and our network is kind of like small, so you'll see things are getting better. Sometimes it's hard to see the difference. So we're going to plot the diff. So diff is, again, these are very small images, so we may need to scale. So it looks like the difference didn't quite work. Maybe you see the difference, but can you see this light gray lines here? Yeah, so that's the pixel difference, all these edges that you see here. So it's training pretty well. It's doing its job and things are getting better. It still doesn't match the original. So that you can see that it's not quite there yet. So essentially you train for a long time and then you may be able to get rid of most of the noise. I think the road picture is, there's slight change in the color as well. So that happens sometimes and you need to figure out the right hyperparameters to tune it properly. All right, so that was denoising. So denoising has other application. We call it denoising, and this is literal denoising because we're removing noise. But you can think of it that you had, say, holes in the images. And then you can fill those gaps by just training. So that's something called in-painting. You can imagine that if you train, instead of denoising training, if you train low-res versus high-res images. So that way you can kind of train for super sampling. So that's another big application area these days because everybody wants 4K images, but sometimes it's wasteful to kind of render these in games. So you can render 2K and then scale them up. Instead of scaling them up where the quality suffers, you can train a network so that the upsampling is what it's called. Upsampling is of a very good quality. So upsampling is reached a stage where I think you cannot distinguish visually whether it's been upscaled using a neural network or whether it's the original 4K. All right, so any questions around denoising? You should try some other ways of denoising. I can give you some examples. So like similar to what you did for add noise, you can say add hole and you can write some code that kind of punches holes in images. You can have a high-res version by, like instead of saying add noise, you can say degrade image, and you can create low-res version of images for training. You can also do this frame interpolation, where you can train 3 frames at a time, where the first and the third frame are the original frames, and the second one is the average of these two. And you can then train to kind of recover the interpolated middle frame from training. So that's another way to train these networks and get some experience with it. So this is something that I'm sharing. So let me go back full screen again. So something to try. So I have these 2 examples where you can downres an image. So this is going to replace the add noise function. We are essentially just scaling it down with a really basic interpolation method called nearest neighbor, and then we are going to scale it back up to the original size. So that will essentially degrade the image. So then you get the downres and the original version. And then the other thing you can try is to adjust color. So to adjust color, you need something with a bad color. So in this case, what we are doing is we're just increasing the saturation. So that would become your bad color image, is the saturated image. So then you have 2. So as long as you have 2 pairs of kind of relatively similar things, you can train them to recover one from the other. So again, they have to be similar enough. So the big idea behind all of machine learning is that as long as you have a distribution that we can match, so all the data that comes in from some distribution that we don't know of. And what we're trying to do is approximate it from a known distribution. Usually we try to approximate it as a normal distribution because we know how to sample a normal distribution. So once we have this matching distribution, then we can sample on the normal distribution, and that would be close enough to the original data. And that's the big idea. I think if you can take away one thing from this whole series of lectures, is that it's all about distributions, and you can think of the world as like all these noisy images, they live somewhere in a distribution along with the cleaned up images. All we are trying to do is find a normal distribution that is as close to that, and then we're trying to sample from that. All right, so somebody asked about like what is the state of the art in denoising. So this was state of the art like 3 years ago, maybe, is UNet, where you have, it's essentially a CNN, and then it goes back up. But in between, you'll see these vertical lines, these things that are connected as well. And that kind of gives it a little bit better quality than a pure CNN. So this thing is called a UNet or a residual network, or ResNet. So that closes the chapter on CNNs. I just wanted to cover a little bit of facial recognition system. How would we build it? Because all these models are great to train, but what do you do with them? So I think we saw some practical advantage for the denoising network, but there is like, to be practical to use, you have to deploy them in something useful. Facial recognition system is one of those things. And if you look at the relatively newer iPhones, so you can see that has a very robust facial recognition system that it uses to unlock it. So let's see how such a system may be built. So again, this is not specific to machine learning. It's just like, how do you build a system? How do you build a system to solve a problem? This is like a very rough architecture diagram of what it would be in this kind of setup. So what we would do is we would have a database of known faces, right? So you have a company, you have registered employees, and you have all their faces somewhere stored in a database. And then you want to install this camera up at the front door, and it will take the image and extract the face out of that image, because the camera may cover the whole body. So you want to just extract the face part of it. And then what you want to do is compare the the extracted face with the database of known faces, and you want to say with some confidence whether they match or not. So the biggest so all these are just software engineering tasks, right? Except for the compare. Like, how do you compare two faces? What does it mean to compare two faces? What about different lighting conditions? Maybe the original faces, the image that was taken was with better lighting as in a portrait studio, but the ones you are taking from the camera outdoors is in shadow. Maybe people are not looking fully face forward. How do you even compare these two? So the good answer is that neural networks can do that. We can train it to compare different images, and it will do not just like an exact match, because that's always going to fail. There's no two people look alike, even from different, because it's the camera differences, because the lighting differences. So this comparison is where we can put in a neural network that will do the job and identify it. So let's look at a little bit more. So this is again in text, what was in the diagram. So there is something called Har Cascades, and that is useful for extracting faces out of images. Again, it doesn't identify anything. All it does is tells you that there is a face in the image, and it tells you this is the bounding rectangle for the face. So you can look up this OpenCV tutorial on the Cascade classifiers. So this particular one is called the Har Cascade. And so this was used, this is not machine learning even, as this is just a traditional feature comparison, image processing things. So after some time, with the proliferation of CNNs and other networks, there was a paper about how to do something similar, but with neural networks. So this is what we're going to use. So we are not going to train this. We're going to just use whoever trained this facial recognition network, and then use it and add in our own data for that. So this particular paper is called Mtcnn. MT stands for multitasking. And the link is again in this slide, which I'll share with you. It does essentially an image pyramid, and it walks through different sizes of the boxes, and like says, is this a face? Is a face? Is a feature? Is a nose? Is an eye? And it knows over time it learns these features, and it returns the coordinates of the eyes and nose and the 2 points on the face and the bounding rectangle of the face. So and the great thing about it is it has already been trained on millions of images. So we don't need to train it even, because it knows what a human face looks like. So it's perfect to use, because we can just put it in and feed it new images, and it will recognize faces within that image. It works for, it's a multitasking CNN, so it doesn't stop at the first face. It will recognize all the faces in the image. So it's even better than that. So, and the second network that we're going to use is something called FaceNet. So FaceNet, what it does, it's a pretty cool paper. If you have time, just read it, because it's a relatively older paper in machine learning research terms, but it's pretty clever in the way what it does. So it's actually a recognition paper where instead of kind of trying to say this person is this exact, like say if it was my face, it won't say this is Rajesh. It will say how different I am from another person. So it's something called a contrastive model, which doesn't give you a yes or a no answer, but it only tells you in relation to two things. So if I have the woman that is here and then my picture, it will tell you how far apart they are. And the way it does is for every face that you put in, what you get out of the model is this long vector. It's a 128 dimensional vector. And it'll get a similar vector for my face. And because these are vectors and these are normalized, it's awesome, because they're kind of like you can do the distance between them like an Euclidean distance. So distance between two vectors, and distance between two vectors will give you basically how far apart these two images are. So, so that's the idea behind FaceNet. And the loss function here is what it is doing is it's taking images that are similar, and then it's giving them essentially, it's kind of trying to minimize that. And then the images that are different, it's trying to maximize that. So that's the loss function, then some added in alpha. So these two terms here, so this one is trying to minimize the similarity, similar images together, and this one is trying to pull the different images apart. So now our system now seems like we can make the system, right? So we get the faces from the ground truth images, you encode them into this 128 dimensional vector. Because vectors are easy to compare, we can just use that instead of images, and read the camera input, isolate the faces, encode the face, and then compare with this vector that you have stored. So compare with all the vectors that you have stored, one after the other, and whichever vector is the closest, that is most likely to be the person. So let's take a look at this file. So this may not run, so I'll make sure this runs once I put it in there, because of this version problems in training and Python libraries and everything. But let's see if we can. So this is going to be a little bit complicated, because of the version differences between different. We're trying to download a model from somewhere. And if it doesn't work, I'll fix it later on. Any questions around facial recognition for this purpose? So just as I want to, this is image-based facial recognition. So it's going to be okay, but it's going to be very easy to fool, because you can just take an image of somebody's face and then show it to the camera, like the old Bond movies, and it will work. So we're going to install the Mtcnn. Mtcnn again does the identification of where the faces are in the image. And we can do something different here. So when you create this virtual machine, or when you connect to Collab, it creates a virtual machine for you, and it's kind of isolated from the world, because obviously Google doesn't want you to put all kinds of weird things in there. So, but there is a way to connect your Google Drive, so you can put in your own files. So I'm going to connect it here. Yes. So this will mount my personal Google Drive into this. And then I loaded the weights that I got from the FaceNet into this directory. So I'm going to load that. And then something happened. Let me import these things again. So it's loading the model. And then I'm also going to download an image from the internet. And the image looks like this. Again, these are not human faces, but I just wanted to show you how good Mtcnn is. So I'm going to run. So Mtcnn is a model that we downloaded. It has this method called detect faces, and you give it an image, and it will give you a bunch of boxes wherever it thinks there are faces. So what we're going to do is we're going to just draw rectangles around those boxes in some color. So I hope you can all see this, right? Yeah, so it did a pretty good job. So it identified most of the faces. So it's a single image that I put, like there are just faces in there. So we ran Mtcnn through that and found all these boxes. And some of the things it failed on are like obvious. Like, so again, this network is trained on human faces. So it's going to fail. It's kind of surprising that it failed on this character from Frozen and all of these. But it still did a pretty good job. So that's what we're going to use. I'm going to use my face so you can see that. There is my image before I had a beard. And then we're going to normalize this image and we're going to encode it. So all we have to do is we have to call face net model predict, and it will essentially return a large vector for us. So now we're going to use that vector. And then we're going to do the same thing with encoding the image. You detect the face and then encode that face. So then we have, when we want to predict, we want to find the closest face, right? So because it's a vector, I can just use the norm of the vector, and that will give me the distance. And then I'll go through all the faces and find the one that matches or has the minimum distance from the one that I'm trying to predict. So this is all wrapped up into one function now, calling all the other ones. So let's try it on an image that I have already stored here. So this is a particular image. Like I've made a collage of 6 images. And so this is my picture from bad lighting, and then different from the one that I gave it. And let's see if it finds it. It should just run this. So it did find it. That's pretty cool. So now we have a very simple facial recognition system, and you can play with this, load other files, and it should work most of the time. Try to make it fail, actually. So that is the more challenging thing. You try to see why is it failing? In what conditions does it fail? Do you have a picture that is not head on if you're looking at the sides, or if you look up or down, or you have different lighting condition, different age of the same person? It should still do a pretty good job, but like try to see what the edge cases are and why does it fail. So that's the job as a machine learning scientist, like engineer. You want to be able to fix problems of the edge cases, because that's going to be, you want your system to be as accurate as possible. Any questions on that? Why do you compare the norm of the vectors instead of the sum of the square difference? It's the same thing, right? It's just a square root there. So you can use either. There is a warning in the beginning of the about TensorFlow 2. Yes, so I know that then because Mtcnn was written for TensorFlow 1.0. So in order to use that, I put in this directive in the beginning that forces it to use TensorFlow 1.0 right here. So ideally, you don't want to use TensorFlow 1 at all because it's kind of on the way out. Brendan has a question. Does this model also highlight where the facial features are? Yes, so it has some other methods. It will give you the features for each eye and nose tip and the two corners of the mouth. So it's pretty good, actually. So you can use it to even track animation if you want. So that is all for this. So yeah, you can look up the API for FaceNet. So we used just the detect faces and the rectangle. Let me show you exactly where it is being called. So when you call detect faces, you get this faces data structure. So if I hover over it, it has 11 items. The box is the first item. That is what we're using. Then it has confidence, and then it has other items that kind of give you the coordinates of the nose and the eyes. Okay, so moving on. So we're making good progress. It's good pace. So let's keep going. Any questions? Just put them up here, and whenever we take a break or the thing is taking a long time to train, we'll come back to this. Where were we? Okay, so this next part we want to cover is something called an RNN. So RNN are like a class of networks which take into account the previous input. So this is like anything you have that is dependent on the previous input. You want to use something like an RNN. So so this diagram should be clear. So it's what it does is when you connect up the network, it also has a line through it where it takes the previous time step into account. So suppose you have a series of images that were dependent on each other, like 3 or 4 frames of a film that you're trying to do some prediction on. You can have the training be joint. Instead of having individual frames, you can connect all your frames together, so you have 3 frames at a time being trained. So the network would become more complex, but it would kind of take into account, say, motion blurring that happens because of movement. So those kinds of things. So, but the biggest application of this is in language processing. When we have sentences and words, they have context in the previous few words. They have more information. So if you just do a word-for-word translation, you may not be able to kind of predict the meaning of the sentence if somebody's saying something. So, but if you take into account the previous few words, you may be able to do a better prediction. So that was the main motivation behind RNNs, and they were used for translation for many of the things. And it can do language-to-language translation. It can do stylistic translation. It can also be used for music, because music is essentially a time series of things that are happening. You can train it for that. So again, the idea is essentially just use previous data at the previous time steps. And there are things that, because you don't want to have, say, the one at ht-1 to have the same effect as the one previous. So the farther things are, you want them to have a little bit of a less effect on the sentence, right? You don't want to have a word that was used 2 paragraphs ago to suddenly have more meaning than the word next to it. So there are mathematical gates, if you will, in here that kind of try to do that, where things would decay over time and things would be kept over time. So you can think of them as things that are like, you're essentially applying more sigmoid-like functions or tanh, where what they do is if the weight is more, it pushes it up to be used. Otherwise, it ignores it. So think of it as kind of electronic gates, but they are just done using mathematical functions here. So so the RNNs advanced more, and then there were some issues with them where things were not kind of were being kept for too long, and like the effect of the previous time steps were being not particularly well defined. So there was the next evolution of that was something called a gated recurrent unit, which does more fancy math under the hood here. It's essentially trying to modulate the weights from the previous time step. So it's kind of taking some mixture of all these things that go in and trying to make sure that the effect is a little bit controllable, so you can choose the values of these functions. So that was the idea behind GRU. We're not going to go into like a whole lot of detail about how that is done. Both these RNNs, I think they've been super popular. They're used everywhere for all kinds of translation. And the next evolution of that was the transformer, which essentially made things much, much faster because they allowed things to be done in parallel. So we'll cover transformer architecture also a little bit, but that's the idea, is like behind all of these three things that I'm talking about, the RNN, the GRU, transformers, is you take previous time step into account, and then you get more context around your prediction. So let's do a quick example, because I want to show you how cool this is, because the language translation problem. So you will see that Google Translate, Alexa, all of these algorithms use similar systems. And then there's app like Google Translate app where you can speak a sentence, it will type it in another language, and then it will convert that back to speech into a different language. So this idea of a global translator is a reality. I think you'll see that in a couple of years, where I'll be teaching this course in English, but then somebody somewhere else is listening to that in a different language real time. So I'll just give you this file so you can practice on it, and because it takes a while to run. So it's a text RNN. What I did there was essentially train the network on a Shakespeare play, and then when you run it, you'll see that it starts kind of first it starts producing gibberish, and then as it trains more, it starts producing text in the style of Shakespeare. So it's pretty remarkable, and it's like a very small toy example, but you can try running it when you get time. So again, this file is in the list of files here in the 15th July. So RNN text. Any questions on RNNs? I've lost my question answer window for some reason. There you go. Okay, no more questions. That's great. Somebody asked about how difficult is it to update the code to run the latest TensorFlow. It's a little bit involved because there's a big API change. And 1 to 2 is a major function revise, right? So it's going to be a little bit involved, but things are much easier, much faster in TensorFlow 2. The Keras API is very nicely integrated, so you should give it a try. So next, we are going to focus a little bit more on the generative adversarial networks. This is, again, an excellent cartoon by Mia. It kind of explains to you at a conceptual level what they are. So generative adversarial network, essentially, what you do is you just take a noise image, right? So you have nothing, you just generate some noise. And then you ask the second network who has seen different images, you say, hey, I think this is a dog. What do you think? And they'll say, no, this is not a dog, because it knows what's a dog, what's not a dog. So because it has been trained on a lot of images of dog. So, and then it will give you some weights, like, hey, this is my current state of weights. And then you'll take that into account, and then you'll adjust your noise to match those weights a little bit. And then you'll show it again to this discriminator network and say, hey, is this now a dog? And they'll say, no, it's not a dog at all. And you go in this loop. And after some time, because of this weight sharing and the network, you start producing images of dogs that the second network, it is not able to tell you anymore whether it's a dog or not, because it's not, because of this weight sharing and training, you are able to produce an image that is indistinguishable from the original distribution. So essentially what you have done is you had no idea of what a dog looks like. You are just giving it a random noise, and you're saying like, okay, keep training. And over time, you are essentially mapping the distribution that is in the original data to a noise, essentially a normal distribution, and you're just refining that one sample into the final image. So instead of finding the distribution and then sampling the distribution, you're just taking a random sample and then adjusting it until you get to a sample from that distribution. So it's pretty cool. It's very hard to train, takes a while, and it's tricky. But we'll try to see if we can do that. So just in text, what I just said now is like, instead of trying to estimate the distribution, we're taking a sample and then gradually refining it until it's the desired sample. So mathematically, it works something like this. Again, you can read that. It's like not anything complicated. It's like the discriminator, as the name suggests, it's trying to say yes or no, and it's being trained on images of dogs, dogs versus cats. It could be anything really. It's just a yes/no network. Like the classifier we did for flowers, it was a 3-class network. And so this one is particularly just a binary classification. And the other function, the process itself, you're just going back and forth between the two networks, training them one at a time. So graphically, it looks something like this. And I think this is a little bit easier to understand. Network, you have the discriminator. So then the discriminator and the generator themselves can be simple networks. They can be, so the generator network essentially has to take a noise and then scale it to be the size of the image. And that's all it does. And the discriminator is a simple classifier, just saying yes or no. And that has been trained on real images. So you train them in parallel, discriminator a few times, generator a few times, and then you kind of let them all adjust their weights, and then you keep doing that. And at some point, there will be a situation where the discriminator cannot distinguish between what you are generating. And that time you say stop. And what is cool about that is now you can take any other noise image that is similar and then feed it to the generator, and it will keep generating more images that look like the original data. So you can have a series of dog images that kind of, they are not from the original data, but they kind of look like that. So very close. So step one, again, it's straightforward. You need a classifier, hook them up together. That's it. So let's see if we can make this work. And I think it's a little bit straightforward to do it on the, if only this didn't keep disconnecting me. So this, I think I wanted to go through this as an exercise, not just give you this, because it also shows you how you can go beyond Keras into TensorFlow directly. So Keras is a higher level API. You do layers and you do the fit method. It does all the training for you. So you know that the fit method is essentially running multiple loops with adjustment of weights, and it's also doing the gradient descent, comparing the losses. So it's all taken care of you with Keras. with the TensorFlow directly, we're going to do this manually in this step because our network is unique. It's not a simple network. There are two networks connected to each other, and there's a little bit tricky to kind of do that. So we're going to dive deeper into the TensorFlow API. Again, none of this is rocket science, and even if it was, we will learn it. But it's like just more API stuff. So we're going to use the digits data that we saw earlier, and that is simple data, grayscale images of handwritten digits, 60,000 data points, and you can smell that size, read the data in. So now this is the generator part. So just to go over this very quickly. So what we are doing here is we are taking in just a random number. We are going to train like 100 images at a time. So we're going to take 100 random numbers. And for each of those random numbers, we're going to convert them to an image. So this is essentially what it is doing is something the opposite of convolution mathematically. It is instead of taking the, remember in convolution, you had this kernel that you would average, say 4 or 16 pixels based on the kernel size. And then you would kind of make the original image smaller, replace that with the averages. You're going to do the reverse here, where you're going to go from one number, one random number, into a little bit of a larger set of numbers. We treat them as image, and then we're going to reapply that. So essentially, you have these 4 or 5 layers. You're progressively making the image larger. So what that does is it creates a bunch of network nodes for you to hang off the weights from, and at the same time, it's kind of expanding from one number to the image size that you want. So that's all the generator does. So again, this is a bunch of just reverse convolution operators called conv2D transpose. And there's some arithmetic that kind of tells you what the sizes end up being once you choose different things. So different kernel size, different padding. So all it is doing is just that. So we make the generator model here, just call the method that we just defined. And we are going to plot. So we generate these 100 random things, and this generator will generate 100 images out of that. And we're going to take the first one and plot it here. So it's just image with random pixels. And so this is the advice I have. Like whenever you do something complicated, just print it out, visualize it, see if it's doing the right thing. So this looks random enough to me. And then the discriminator one is, again, a simple convolutional network with 2 layers. It's just a classifier, right? A dense node output of 1, which is just a yes or no binary. Let's make this. And then we're going to define our losses. In the classification, we use the binary cross entropy, and then our loss. So this is kind of, so our loss in the case of discriminator, the discriminator is going to maximize whether things are true or false. So, but at the same time, it is going to also minimize so it doesn't want to let the generator win. So it's going to maximize that and minimize this. So these are the 2 losses that we add up, and this is what the discriminator is going to do. And the generator, on the other hand, is going to want to fool the discriminator. So it has a loss, which is the opposite of this particular loss. And we define some optimizers. Again, optimizers don't really matter, but just to give you examples. So because this is going to take a while, so we're going to create these things called training checkpoints, because you don't want to come back half an hour later and say, oh, Google killed my machine. So this training checkpoints is, it will write the weights out to disk. So you can pick up training from where you left off. It's also how you would finally get your data, your model out if you want to move it somewhere else. So these weights can live on. So now we're going to train. And again, as I said, we are going to kind of not use the fit method. We're going to go into the nitty gritty of what the fit method does. And we do a manual training here. So instead of showing you the train step, let me show you from the top. So we are going to write a for loop. We're going to go into each of the epochs. We're going to take the batch of images and train it. And the training step is defined here, where we are essentially, with all the gradients that we get, we are going to compare the losses and find both the losses, and then let the gradient descent happen by computing the gradient, and apply the gradients, and that's it. So this is the loop that the fit method does normally, and we're going to do it manually here because we need to do all this loss computation collectively together, because the generator and the discriminator, they're being trained together. And let's run this or define this. And then let's do the training. Again, these are just methods. So this is where the training will happen. Okay, so this will go on for a while because and then we'll come back to it and see, because it will need to have some images there. It's also sometimes cool to see what is happening. So you can see random images in the first, just converging a little bit to the actual data set. These don't look like digits yet. So we'll wait for another epoch. So epoch 2, it's a little bit better. You can see something is forming, some structure is forming from the random pixels. And this is when I saw this years ago, this is what got me into the field, because this felt like magic. And it's further converging into these shapes. Okay, so let this go on. Let's get back to the webinar part. So I'll give you these links in the example you can use. There are some nice applications now online that you can try. One is called the Ganimals. The other one is a Gogan, which is a very clever name. Both are really good things to try on. Again, you also get some information on how these things work. You can check them out. So let's move on. So we don't have much time. If we get some time left over, we're going to come back and cover some more of this. So I briefly mentioned transformers, and I'm just going to cover the architecture of it. We talked about transformers in relation to text data and data that is dependent on time. So what actually it does is essentially a decoder and an encoder. And it takes the text, encodes that in some kind of a position, because you cannot use text in neural networks. Everything has to be a number. So you want to encode it. So it's a positional encoding, which tells you where they are in relation to other words, as well as some code for the word itself. And then it kind of encodes that into, you can think of it as a autoencoder almost, and with attention, which is what RNN was. So this all goes into some latent space where you have this relationship between words and their positional data, and you essentially train it together, and you compare it with the final output, adjust your weights as normal, and it works. So you can do translation, and as long as you have the ground truth, so you have these dictionary, not dictionary just of words, but dictionary of phrases that you can then map against each other. So you can essentially translate from one language to another. So the cool thing about this is that the script doesn't matter, right? Because for every language, there is some encoding, some ASCII or UTF encoding that is there that you can use. So you can translate from English to French, which uses the same letters mostly, or you can translate from English to Persian, which uses a totally different set of characters, but they all have some encoding underlying, so you can still use it. So it's pretty cool. And the major advancement in the transformer was the way they structure the network, where it can be parallelized. So as things like progressed, transformers became the dominant network for any kind of text-based things or any kind of sequence-based things. And then somebody discovered that we can use it for other things as well. So right now, transformers are the dominant networks in all machine learning research and work that is going on. You've probably seen like all the Google search is powered by something called BERT, which is transformer based, and there is the OpenAI that model that was recently acquired by Microsoft that is in now Visual Studio that does code completion for you. In fact, it even writes large pieces of code for you. They're all based on transformers, and it's pretty cool. So the one thing is that like all large usable networks, they are super large. We're talking like billions of parameters and weeks of training on things that only Google and OpenAI and Facebook and NVIDIA can afford. So it's a little bit out of reach of normal people like us. We can still use some cloud-based GPUs to run these things, but to be able to compete with that, to be able to train these very, very large models, it's become like it's in the hands of a few. It's a little unfortunate, but that's how it is. So large models are pretty good. We're going to look at something, maybe before that, let's go into the diffusion. So diffusion is another model that is very popular. It is similar, you'll see that it's similar in structure to a GAN, but it runs, it's more tractable than GAN. So GAN can have this problem with something called vanishing and exploding gradients, where you'll see a vanishing gradient is nothing but when the gradient becomes too small, it's kind of stop having any effect on things. And the exploding gradient is the opposite problem of that, where you have too large a gradient and is having an oversized effect on the final prediction. So this diffusion kind of fixes some of that issue. It's a little slower to train because of the way it works. So again, it's the similar philosophy. You start with a noisy image. Actually, you do the opposite. So what you do is you take a clean image that you then slowly denoise over time. So you can have this noise L2, noise L3, noise level 4, until it becomes pure noise. So now you have a way of going from clean image to pure noise, and then you train it to go the other way, right? Because now you have like ways to go back as well after training. The good thing about that is because you can choose the step, like how much to denoise in each, or how much to add noise in each step. It's a very gradual process. So you can learn that from one to the other easily, and then from next to the one after, and then ultimately you can learn to create the original image. So now that you can go back and forth, what you can do is you can put in a different noise, slightly different noise, and that would give you a very similar image. It's not in that, but it's going to give you a similar image. So it's a pretty nice model. A lot of things are using that. It's kind of supplanted GAN in some way for this kind of generative image out. So let's take some more questions. So some questions are general, right? So we'll have these questions because I think you haven't tried training networks. So I think questions around like, what is the network size? And why should I have more nodes versus less nodes? And I keep saying it's an art form, but it's also when you are in the weeds, I think that's when you realize the effect of it. I mean, you are going to monitor your training loss and how it's going down, and you're going to adjust these hyperparameters. So until you are like gone through that experience, it will sound like magic to you. But once you get in there, you understand like what effect it's having on a particular model that you're choosing. It's very data dependent. It's very model dependent, all these hyperparameters. So you need to adjust them. I can't just give you a number saying, hey, 32 is great. I mean, these numbers work for smaller networks like we've been practicing with, and any number will work. It should be fine because they're so small. So another question about, can you train a network to extract important frameworks from business books? What network is best suited? Yes and no, because somehow I think you have to formalize your problem statement, right? Like what kind of information you want to extract, what kind of frameworks you're talking about. Is it HR, or are you talking about financial models? So you can, so as long as you are specific, like you want to be as specific as you can and you can train with that specific data, you'll be great. If you're trying to solve a very big general problem, you need to train like Google or OpenAI with billions of parameters and internet worth of data. So if you have a specific problem, this is great. I mean, you can solve it by yourself. You have the exact data you need for your specific problem. But if you're trying to solve a very general problem, you're going to have trouble getting the right kind of data to train with. Okay, so now we covered diffusion models. We're ready to go into some of the commercial things that I talked about. So this is DALL-E 2, and what it does, and hopefully everybody has heard about it for now. If you're interested in this field, you type it some prompt, a text, and it will tell you or draw you an image based on that. And this image doesn't exist anywhere else. It's a particular image that it will figure out. So these are some of the examples of astronaut riding a horse. So it's pretty cool. So I have access to DALL-E 2. If you want any prompts right now to generate images from, let me know. I'll log in and we can have some fun. So just one-line prompt. So it should look something like this: astronaut riding a horse in a photorealistic style, or a teddy bears lounging in a resort as a pencil drawing. So something like that. So just type it in the comment section or the question section, and I'll see if I can generate this as we go along. So how is this DALL-E made? Like, so it seems like magical. So it is magical. So it's in a way, it's a effort from multiple people with multiple kinds of networks all put together. So the main things that are happening here is, let me see if I can draw today. Annotate, draw. So there is something called a clip. It's horrible. A clip network and a diffusion model that we talked about earlier. And what clip is it takes text as input. Okay, I should not even have tried writing. So it takes text as input, and instead of classifying so image with text. So all these CAPTCHA things you have been doing, like when people ask you to find bridges or aeroplanes or roads, Google has been taking in that data and learning from it. So it takes these image with captions, and instead of kind of learning to classify. So if you give it a new image, instead of learning to classify, what it does is it does something similar to what we saw in the Mtcnn. It does a contrastive loss where it pushes images and text that are close to meaning to each other in one direction, and then things that are different from each other in the other direction. So essentially, it learns to find out what similar things mean. And this text is encoded in a way where, so there are different ways of encoding text. So one of them is around meaning. So when you say walk, a word like walk, and then feet. So it's somewhat related. It's not really related, but all these words, they are going to be close to each other. Unrelated words are going to be farther apart from each other. So over time, what you do is using this encoding and contrastive learning, you would find similar images with similar captions closer to each other and other ones farther from each other. So now you're going to train, after you've done this, so this is your first model, and then you take a diffusion model that we just saw. It takes a random image and then takes your text prompt and then tries to find the closest things that are in that image and the set of prompts, and this tries to generate that. So it does that by something called conditioning, which is you can give, so if you look at what we did in, for example, in the diffusion, we went from image to noise and noise to image. So instead of just using noise, you can use noise plus some condition. So it can find an image that is similar to that you gave. So, so by using this process, you can, first of all, like make things go faster, but it also goes to find image that you have given as samples. So that's all there is to that. Let's see if we can generate something. Okay, I'm going to just take the first one because you don't have much time left. Clear my drawings. Okay. Woman with 12 hands holding different horoscope signs in each hand. Okay, let's see what happens. So it's pretty quick to, and not only that, it gives you 4 images. Is that what you expected? Pretty cool, huh? Okay, I'm gonna do one more. I'm gonna send you this image if you want. Put in your email in the chat and I'll send you the image. We'll do one more and then we'll wrap up in the next 2 minutes. Is that good with the flying cars and the green? One more. That does look like Andy Warhol paintings. Okay, last one because it's so bizarre. A request, circular capybara. What does that even mean? That's not circular at all. So this store all the things that I generated in the past. So this one was the coolest because it did I asked for a tennis ball Just wanted to see how nicely it merges the texture. So you look at that, it's beautiful. So you can't distinguish it from like tennis ball as it merges. Okay, so this is great. We are at the last slide. So in summary, we learned a lot. We did the basics, different kinds of networks, did autoencoder, CNN, talked a little bit about RNN. LTSM is just another form of RNN. Talked about ResNet and UNet a little bit, variational autoencoders, transfer learning, GAN, diffusion. Awesome. So in practice part of it, we covered bias, variance, overtraining, undertraining, overfitting, underfitting, data that you need lots of it. You can augment it. You need to be unbiased. So the key phrase is it has to be equiprobable. Like you want all your data points to not be so different from each other, so that they don't belong in that distribution. So independent and identically distributed is the key set of words. Hyperparameters, you talked about that a lot, layers, nodes, optimizers, learning rate, loss functions, we talked about L2, L1. L2 is nothing but mean square loss, and L1 is the mean average error. And we talked about log likelihoods and how they're all the same ultimately. Training, what it means to do epochs, difference between batches and epochs. We learned about TensorFlow data system. We learned some matplot and seaborn plotting, distributions. Again, this is one thing you can take away from this course is this. And some advice that you want to work like a scientist. You want to hypothesize, experiment, observe, record, change, repeat, and keep doing that until you're satisfied with your answers. And a lot of things we did not cover. We did not cover a cloud-based, how to provision these machines, although this VM that we are using with Colab is actually cloud-based, but there's ways to get more machines, powerful machines to train. We didn't talk about details of MLOps much more than what we covered for the class, clusters of machines and environments. TensorBoard for logging and visualization. So there's another tool from Google that is pretty nice. We didn't cover that at all. Intermediate layer visualization, again, it takes a long time, so we didn't cover that. The latent space visualization. For other methods other than neural networks called random forest, XGBoost, very useful for table data. We didn't cover reinforcement learning, where you train an agent based on the state they are in, and the environment they're in, and what reward they can get when they move to the next state from a possibility of multiple states to move to. And then everybody wants more theory. So you're not going to become an expert by attending this 3-part webinar. It will give you enough of the idea of the entire field, where your interests are. You go maybe try out these examples that I have, execute the scripts one line by line, and ask like, why is it doing what it's doing? Look up the API. It should be fine. And here's some way for you to, if you don't have access to Colab, which pretty much everybody has, but if you want to, if you have a powerful GPU at home, you can do this at home by setting up a Python-based environment. And I have the slide there to kind of tells you how to do that. I'll put this slide deck right after this class is over. Where to go from here? Books there, free books all over the place, free tutorials. Statistics is the key to a lot of these things. You need to have a strong base in that if you want to do more research. And a lot of good video tutorials from 3 Blue, 1 Brown, and there's a bunch of books and free books all available to you. So not going to go too much over time, hopefully. Any questions, closing thoughts? You can, again, contact me on Twitter or LinkedIn. I will answer your questions, so if you have any. All right, end in 1 minute if there are no questions at 1:35 p.m. Pacific. And thanks again to everyone for being here, and keep learning. Thanks to all the people working behind the scenes today and in the previous classes. Thanks to SIGGRAPH. This has been great. And if you want me to cover something else in more detail, again, each of these subtopics probably worth their own lecture series. But if you get stuck in something that you want to see, there are things like when you add in, like if you're coming new to this field, so there's the theory, there is the conceptual ideas, there is the math, and there is all these software toolkits and APIs, and it can get complicated. So don't get overwhelmed. I think just narrow down your problem set. So you can have one data point and you train your network, it should memorize the data after a few minutes. Like if you have just one data, keep feeding it over and over again, it will memorize the data. So you will at least know that your network is functioning, it's doing something. You want to keep verifying at each stage, and as you get better, experiment with bigger things, go to the cloud, load larger sizes of data, download other people's network. So if for people who don't have access to DALL-E, there is a DALL-E Lite, which is from Hugging Face. So Hugging Face is great, actually. So it is, let's see if it does better in customer circle. Let's see if this does better. So this, you can go to this website, huggingface.co. It has a smaller version of DALL-E, which they trained. So it should give you similar answers. All right, and hope to see some of you at SIGGRAPH. And goodbye, and see you next time. Bye.